the third in a series that we have had this semester. It's my honor to introduce my very good colleague, Carol Espy-Wilson, and I'm very pleased that she decided to give this talk today. Carol, as you know, she's a professor in electrical engineering at ISR. She received her bachelor's degree in electrical engineering from Stanford University in 1979, and then she received her master's and PhD from MIT afterwards in she finished around 1987. Carol's research is in speech communication, combining knowledge of digital signal processing, speech science, linguistics, and acoustics to conduct interdisciplinary research in speech recognition. And we're going to hear about some of this today. Of course, Carol is the recipient of many prestigious awards. She's a fellow of the Acoustical Society of America. She is the chair of the Speech Technical Committee of Acoustical Society of America. And very recently, I was teasing her the other day because there are a series of awards that her group has received, including being the MTech finalist team for the University of Maryland 75K business competition. Her undergraduate students received the prestigious NSF recognitions for the most interesting project and most technically challenging project that they conducted. And one of her graduate students very recently received the Best Dissertation Award in Electrical Engineering. With no further ado, I'm going to let Carol start her seminar.
Okay, well, thank you for that nice introduction, and welcome everybody. Today I'm going to be talking about speech and try to give you a sense of why we have not gotten to the holy grail of speech. And one of those would be in terms of speech recognition, where you could talk to a computer like we talk to each other. And so hopefully you'll have an understanding of why this has been such a hard problem. It continues to be a pretty difficult problem. And so there's just a lot of areas in speech that still need a lot of people to join and do research. Okay. So Bill Gates said back in 1999 that speech is not just the future of Windows, but the future of computing itself. That is because speech is the easiest mode of communication and the fastest mode of communication that we have. And so instead of texting and using your thumbs a lot, you could just talk to your machine. That would make things a lot easier. Also, the MIT Technology Review in 2004 listed universal translation as #1 on their top 10 list of emerging technologies. And this is a technology that needs speech recognition. The idea here is you want to be able to speak into the translation system in one language, have it understand what you said, and then it produces synthetic speech to say on the output in a different language. So it would just allow global communication. And recently, Google just announced that in a few years they hope to have a speech-to-speech translation system on their phones. So that's another very hot area of research, and there's a big group here at the University of Maryland, actually in the computer science department, that is working on machine translation. Okay, so just to give you an overview of some of the current projects in my lab, one of the projects I'm going to be talking about towards the end of my talk today is on robust articulatory-based speech recognition, which is being done by a graduate student, Vikram Panitra. I'm also hoping to get to talking about the speech enhancement and speech segregation work that we're doing. This is the subject of the business plan competition. This work is being done by Shrinkam Vishnubatle and Vijay Mahadevan. And then a very new area for us that's very interesting is this forensics area, doing source identification of the channel, what type of phone are you talking through, or whether it's a cell phone, landline phone, or a standalone microphone, and media authentication. If someone has modified your signal on the internet, being able to tell that those modifications have happened, and that's been done by Daniel Garcia Romero. One of my PhD students who has finished is now back doing a postdoc with me. And we're working with people up at the University of Maryland Dental School to look at patients who have had glossectomies when they have a part of their tongue removed. We want to try to build a tool to help surgeons how best to do that so it doesn't, to maximize speech intelligibility once that procedure is done. And then to improve another one of my ex-PhD students who's now doing a postdoc with me is looking at SNR-dependent speaker identification using unclean data. So when you don't have clean data to build models, you have to work with unclean data. How do you do that? And how do you do that on the fly? And build good models so that you can do reasonable speaker identification. And then lastly, Jaime Hernandez is looking at speaker recognition and trying to come up with new features to improve the performance of speaker recognition. Okay, so first I thought I'd give you a history of what's been going on in terms of speech, in particular speech. Well, there's some synthesis and recognition stuff here in the slide. So back in 1779 was the first mechanical synthesizer. So you can see research has been going on in speech research for a really long time. The first toy that came out with speech recognition was Radio X back in the 1920s. It didn't work that well, but it was first attempt. Another important date is in 1946 when they invented the spectrogram device. That was really key because that allowed us to visualize speech, to start to recognize special properties of the speech signal. And my contention is that you do not want to treat speech as if it's just any signal. It's a very specialized signal. Okay? Then Bell Labs, which was haven to work at for many, many years, they developed this first digit recognition system back in 1952. Then in 1953, we had these distinctive features that were developed by linguists. And I'm going to talk about that because that provides a framework for the kind of research that I do. People started looking at grammar probabilities. What's the probability of this word happening after another word? In addition to using acoustic information to do speech recognition. So using higher level information back in 1959. And this was pivotal. In 1960, a book called The Acoustic Theory of Speech Production was published. It was written by Gunnar Plott, and it really gave us a way of viewing this whole speech production system as a system and how to break it apart and understand different components. And then we had these very nice signal processing techniques developed as an alternative to Fourier transforms, cluster analysis, and linear predictive coding speech came along in the 60s. Those are sort of the front end of parameterization of the speech signal that you want to put into speech technology. And ARPA, the Advanced Research Project Agency, started in 1971, this 5-year project on speech recognition, and that's where we got an explosion of a lot of people, a lot of different sites working on speech recognition. And the approach back then was largely influenced by artificial intelligence. So using a lot of knowledge-based information to do speech recognition. Information like the things humans are doing, trying to put that into systems. Along came hidden Markov modeling that on the heels of this project, and hidden Markov models is still the current state of the art in terms of the back end for recognition systems today. The first textbook on digital processing of speech signals came out in 1978. We had this is important, in the 80s, we had a lot of other signal representations developed that was auditorily inspired. And then another big opera project in 84. At this time, HMM was the dominant approach back in for the speech recognition at that time. This HMM work started at IBM. And then, up until this point, people have been doing recognition on isolated words and, mainly isolated words or really constrained grammars. Now in 86 was the first time that we had a large database that was collected to try to standardize research so that people could compare different recognition systems developed at different sites using the same data. So you knew you had an apples-to-apples comparison. This was the tenant database called tenant because it recorded at Texas Instruments, and then transcribed at MIT. And this was like 630 speakers from all the 7 different regions. They broke the U.S. up into 7 different regions and had an 8th region for people who traveled around because they were Army brats. And that led to the formation of this linguistic data consortium that now has a whole lot of databases for various recognition tasks. In year 93, we got spontaneous speech. We've been from citation speech to read speech to considered database. We're now working with spontaneous speech. And that's a whole other set of problems you have to deal with when you go to the spontaneous speech. Because now you have disfluencies like, those kind of things, non-speech sounds, so non-words being said. And then we started these risk evaluations on speaker recognition. I thought I'd mention those because that's a very important evaluation that's done, I think, every year to evaluate speaker recognition systems. Speaker recognition is getting, or has been getting, a lot of attention as much as speech recognition, especially with Homeland Security and other issues. Okay, so first I'd like to just give you an idea of where we are in terms of automatic speech recognition relative to what humans do. So here I'm comparing the performance of human recognition and ASR on a spontaneous speech database. And you can see there's quite a bit of difference in performance. We're looking at the error rates. Okay? Here I'm looking at how recognition performance varies as a function of the signal-to-noise ratio. How much noise is there in the speech signal? And again, you can see that humans way outperform automatic speech recognition systems. So this is just pointing out that we still have a long way to go. We've made a lot of progress, but there's still much to be done. And this is showing the effect of channel effect, whether you use a high-quality microphone or a low-quality microphone. How well are you doing in terms of speech recognition? Again, humans way outperform automatic speech recognition systems. The reasons for these performance gaps, in my opinion, this is my pet peeve. I think that there hasn't been enough attention focused on the speech signal itself and how much information we can pull out of that signal, especially in trying to remove the mass amount of variability there is in the speech signal. And I'm going to spend a lot of time talking to you today about all the variability that we have in speech. Also, we have to deal with everyday environments where there's going to be all kinds of different types of noises, there's going to be reverberation, and then you have the channel effects. And I just showed that to you with high quality, low quality comparison microphones. And then you have to deal with those disabilities that I talked about when you're coming with spontaneous speech. Okay, so first I want to go through this whole speech communication chain just to give context for understanding the problem. So when a person is ready to communicate, they start off with discrete units. Those are the words that you want to say. And, you organize them according to your grammar here in your brain. That the brain sends signals to activate your muscles to actually produce those words. So you go from these discrete words to this continuous signal that comes out. And then that pressure wave is peaks on your ear. And your ear does a lot of processing of the speech signal. One thing we know is that the ear is most sensitive to the frequencies in speech, which is sort of in a mid-frequency range. So this production system and the hearing and perceptual system have probably evolved together to take advantage of one another, to work and co-work together. There's quite a bit of processing that goes on here, so that things are transmitted in terms of the firings of the auditory nerves, and that goes up in the auditory cortex in the brain. And Professor Shaman is here today, so I'll come in. He does a lot of research here and understanding what's going on, once you get past the ear, going up into the brain. My work is focused more on understanding the relationship between how you move these articulators around and how that is manifest in the speech signal. So what I'm going to talk about a lot today are different algorithms, signal processing techniques we have developed to pull specific information out of the speech signal that we think will be important or speech recognition or speech recognition. Okay, so, and let me just mention, well, I've already talked about the background of that, but so here, when you're doing this theory, and the reason we really want to understand this process, and again, is because humans are the best speech recognizers. So the more that we can understand about how we're doing it, the more it can influence these automatic systems, and hopefully we can narrow the gap between human speech recognition and automatic speech recognition. Okay, so now I want to give you an idea of the various articulators that we use when we produce speech that are really important to how sounds are produced. First, down here behind the Adam's apple are these vocal folds that either can vibrate periodically or they can be spread apart. And so these vocal folds modulate the airflow from the lungs up into the vocal tract. So it provides an excitation to the vocal tract. Now, the shape of this vocal tract will determine what the resonant frequencies of that vocal tract are. And the shape is determined by what you do with your lips, your tongue, and various parts of your tongue. You can move just your tongue tip, or just the middle part of your tongue, or you can move them together. You can move the root part of your tongue back here. We have this deal here which can be raised so that airflow goes only through the oral cavity, or you can lower that deal and you can have airflow through the oral cavity and through the nasal cavity, or you can make a closure somewhere in the oral cavity so air can get trapped here and then air can only pass through the nasal cavity. So there are a lot of things that we can do to change the shape of that resonator. I haven't actually moved the tongue around that much here, but there's a lot that we can do. You'll see some pictures later on. Okay, now I also want to introduce a framework that will help us in understanding my work. And this framework was developed by linguists. It's called phonetic feature theory. And phonetic features are the smallest units that distinguish one sound from another sound. So, for example, if I compare the initial sounds in cat versus bat, those are produced in exactly the same way, except in one case I vibrate those vocal cords, in another case I have them spread apart. That's the only difference when you produce those sounds. And that is captured by one feature that's called voicing. Voice, if it's voiced, vibrating, if it's unvoiced, I have the vocal cords spread apart. Okay, so they are the minimal units that distinguish between sounds. There are 20 of them that characterize all of the world's languages. Any one language may only use a subset of them distinctively. And they are related to what's going on articulatorily in your vocal tract. There are 3 categories of them. One is talking about manner of articulation, that is, how open or closed is your vocal tract. The second set is talking about place of articulation. If you have a closure or narrowing, where in the vocal tract does it occur? That's the place. And then the source is just talking about whether you're vibrating those vocal cords or not. So there are these 3 sets of phonetic features. Okay, I have them listed here. I'm not going to go through all of these. But I just wanted to point out here that all of the sounds in American English are here at the bottom, except for the vowels. I just left them here because there's not enough space to put all the vowels. So I left it as one category. Okay, and in English, every consonant has a voiced counterpart where the vocal folds are vibrating, or an unvoiced counterpart where they're spread apart. So there's the puh versus the puh, or the duh versus the tuh. Okay? And what distinguishes these guys from each other is where you make the constriction. For a puh, we call that labial because it's at the lips. Okay, so this is telling you where in the vocal tract you make the distinction. So the green ones are those place features. The red ones are those manner features, and I'll give you a sense of those in a few minutes. And then these are the vowel features, the voice. Everything on this side is already voiced, so you don't need to make a distinction here. And here they can be voiced or unvoiced. The manner features are most robust. They're robust up until minus 18 degrees signal-to-noise ratio. You can still detect this very well. But for the place features, it's only robust up until plus 3 degrees signal-to-noise So now let me go to the source filter view of speech production, because there's a groundwork, again, in addition to the phonetic features for understanding our work. So the speech signal can be thought of as that excitation for most sounds coming from the glottis, the vocal folds vibrating or not. That signal goes into your vocal tract, so you have a convolution of this excitation in the vocal tract. Then it radiates, so you can represent the radiation of another system. And then you get the speech signal. So you have this convolution here, or if you go into the spectrum over here, you're multiplying those spectra together. Okay? So just to show that to you, here's, we're contrasting two sounds here. This is the sound, like it's supper. That's a vowel sound. Kind of a neutral vocal tract here. And then the sup and supper. To make this sound, you have a narrow constriction here. That generates a loud noise. That noise right there. Okay? So the source for the is here at the glottis, where the vocal folds are vibrating. The source for the sub is above the glottis, here formed by that constriction. Okay, so the location of the source is different. When you have a voice source, because of this periodicity, you all remember your signals and systems. That's going to give you a line spectrum. Okay? And it's very low pass in nature. This falls off like 1 over F squared at high frequency. Contrast that with this source that's produced up here with this narrow constriction. That's a noise source. So there is no line spectrum. It's continuous and it's fairly flat. Okay? Now, given this vocal tract shape, which is very neutral, you have these almost evenly spaced resonant frequencies. In this speech, we often call these form frequencies. So this is the first form of frequency, or F1. This is the second form of frequency, F2, and so on. Okay, since the source here that the glottis is inside all of vocal tracts, so you see resonances starting at very low frequencies going all the way up. However, this source, which is further forward in the vocal tract, just excites that part of the cavity in front of it. And since this cavity is very short, the first resonant frequency that you see is very high. Okay, so you get a peak all the way up here, between 4 and 5,000 hertz is your first resonant frequency. The rest of them have been canceled by zeros. Okay? And here are the radiation characteristics that are the same. And this is the resulting power spectrum of the speech signal. So you can see that the harmonics that you have here in this voice spectrum, the amplitude of those harmonics get changed by the vocal tract transfer function. Okay? Okay. So just to point out what those phonetic features say. So here we say, given this periodicity, this line spectrum, we call that voice. Can you see that? Oh, sorry. However, over here, since this is flat, we call that unvoiced. Here's another phonetic feature. Sonorant means I'm exciting all of the vocal tracts, so I have energy from 0 all the way up to 5,000 hertz here. Non-sonorant, since I have my sources above the glottis, I'm not going to have energy down here at low frequency. My energy is going to mainly be up here at high frequency. So that's a non-sonorant sound versus a sonorant sound. Okay. Now, let's discuss spectrogram. Remember I said the spectrogram machine was developed in 1946. It was very important because it allowed us to visualize speech. So here's a time waveform, and this is a spectrogram where, again, you have time here along the horizontal axis and frequency along the vertical axis. The darkness here represents how much energy there is in the signal for these different frequencies. And as you move across here, this person is saying she had the dark signal, you see water all here. That's one of those tendencies. Okay, what you can see at the outset here is the signal is changing a lot. This is definitely a time-varying signal, and the properties are changing quite a bit. We have regions here where there's a lot of energy, and it's mainly up at high frequencies. We have other regions where most of the energy is down low. You can see the movement of the resonant structure here. Here's the first resonant moving along. Here's the second resonance moving along. And that second resonant frequency is the one that moves the most. And it can go as low as 600 hertz up to 2,500 hertz. That's a wide range of movement. Okay? And if you look closely, you can see these vertical striations occurring here. Those vertical striations are because the vocal folds are vibrating. That's the periodicity. But in these regions, you don't see vocal fold vibration because these are noise regions, like Okay, so just pointing out, no vertical striations, non-voice, vertical striations, voice. Oh, here I'm contrasting a continuous sound because that's a steady sound, that's nothing changing. But if I make the sound like dog at the beginning of the word dog, that's called a transient sound, because in order to make that sound, I have to have a period of time where I'm building up pressure behind. I completely close off my vocal tract, I build up pressure, and then all of a sudden release it, and I get this transient that you see right here. So that would be called non-continuous versus continuous. And then I'm contrasting two places of articulation. This is the sup or zup in Greasy. You can see the energy starts here around 3,500 hertz, whereas in the sh in wash, it starts here around 1,500 hertz. And that's because the length of the vocal tract is different, given they have different places of articulation. The constriction is further back in the vocal tract for the sh than it is for the sup. So just pointing out again a place. Okay, so now I want to start talking about variability. I realize this is so hard. So first I'm going to show you, we have a lot of different voice qualities, but they can be broadly categorized into these three. This is a creaky voice. I'm going to demonstrate and play that for you. Oh, I forgot to play it in. A recorded measure that can tell you about which one of these voice qualities you have is the difference between the first harmonic and the second harmonic, which is largest for the breathy voice, because this is more sinusoidal, the swallows off a lot faster than it is for modal voice. And then for creaky voice, they either are not different, or the second harmonic will be greater than the first. However, even though these are reliable cues, getting at that information can be very hard, because in order to do this, we have the inverse filter of speech signal, which is not easy to do reliably all of the time. And in fact, we did remove all of the formats. You see this little bump here should have been there, and so you get this little clip here. So trying to figure out where, and the thing is that to inverse filter, you want to, it's best to do that when the glottis is closed. Remember, it's vibrating. If you can get it from just the part where it's closed, so you don't have the coupling to the subglottal system, you get a better estimate of the glottal waveform. So this can be very hard. Alternatively, we developed in our lab an A-period, C-period, and pitch detector that can also give us information about which one of your voices you are. The blue region, this is again time, and this is frequency. And in each time frequency cell, we decide whether it's periodic or aperiodic. And for modal voice, you see more blue than anything else. For breathy voice, the breathiness often gets manifest up in this high frequency region too. In this case, your vocal folds aren't closing all of the way, so you always have this constant airflow exciting the vocal tract. And it's exciting on higher forms. And so you can see more red up here. And in creaky voice, you can see the irregular spacing of these vertical striations, and we developed a creaky detector as well. So that's just giving you an idea of some of the signal processing that we do in the lab. Now that parameter not only does that, but it's also good at picking up other kinds of variability in the speech signal. For example, this is in the speaking rate. This person is saying every day very clearly and then very fast. So here, every day. Here, every day. Okay? You hear them both as every day. But what happens in this case is because they're speaking fast, they don't reach their target all the way when they're talking. And so they don't make the constrictions as narrow for the B or for the D as you ordinarily would if you were speaking very clearly. As a result, you can see these guys look like totally different animals than what they do over here. I mean, they look like completely different sounds, but you still hear them as a B and a D. You have no trouble understanding these words. And we can pick up that difference here between these sounds with this room. So the trade-off is between how much voicing versus noise we have. Because this guy, and I should mention this, I said that some sounds are produced with vocal vibration, some you make a constriction further forward, then there are some sounds that have both sources. And you're trading off which source is most, is primary. Here the noise source dominates. Here the periodic source vibrates because you don't make the constrictions on there, so you're not generating more. I don't know how to bear with you, but I can try. I'm not hearing it at all. Oh, wait a minute. So here you go. And then this one. You hear the vocals every day. Yes.
So you phase the code at clear, spoken sound, and speed it up. So you used to go up to like 2 or 3 times faster and still understand it. But is the upper limit for speaking out the same for this fast speech?
Oh, how quickly do people speak? I actually don't know if you get 2.5 times faster. I doubt it. You get that fast. And the duration of things isn't consistent. The consonants are reduced more than the vowels are when you're speaking faster.
This is a beautiful example of example whole, even though the part.
Yeah. Well, there are other cues to this, so that's why you're doing it. Okay. Okay, and then this is just showing that you have different speakers have different idiosyncratic behaviors, different articulatory habits. These are 3 people saying very clearly the alphabet C. And here the Z is totally a noise source, so it's in green, voicing is in black. Here the person transitions from being a voice to a noise source. And here they are both noise and frication throughout. Okay, so that's just picking up different articulatory habits. And that parameter is lucrative. Okay? And this is just showing how well it works. You can see it works pretty well. I'm just trying to speed up. And one thing we're able to learn from this parameter is that this happens when you have these voice obstacles that have a noise source and a voice source. Canonically, they always been thought of as being just the noise, being dominant. But we were able to show that many times you have both sources being equally strong, and then a lot of times it's the pure source that dominates. So there's a lot of variability that goes on in speech. The variability I just pointed out happens a lot when people are speaking very casually. You get a lot sloppier, and you just don't reach those targets. So I'm going to slide through this a little bit. This is just to show you some of the very basic fundamental research going on in our lab. This was looking at American English R sound. This is a very complicated sound for a lot of people to learn how to produce. And we did not have really good models for trying to understand the production of these sounds. So we did it. We figured it out. And many people have thought there was a many-to-one mapping for this sound. What that means is all of these are magnetic resonant imaging of 22 speakers all producing R. And I hope you can see they can be very different in terms of how they shape the vocal tract. I'm going to just highlight 2 of those. This is the retroflex R, where the tongue tip is up, tongue body is down, and this is just the opposite. Tongue mid is up, tongue tip down, but they are both R. What's important is that there are 3 constrictions made along this vocal tract. You have this narrowing at the lip relative to this large volume behind the lip. And somewhere along the palate you make another constriction. Here's with the tongue tip, here's with the middle of the tongue, and then in the back part you have this narrowing. So even though people are using different parts of the tongue to achieve different things, those 3 things stay the same, which is why we always hear them as an R. But anyway, we were trying to get information that would help us distinguish when people are producing it this way and that, or this way. The reason is because people only produce it one way or the other. Rarely do you find people who can flip between one and the other, even if they're trying to, because you're not thinking about it. And so this is a good speaker recognition cue if you're trying to confirm that someone is who they say they are, right? Because even if they are trying to fool the system, this is not something they can do to fool the system. Okay, so what we found in our study, and I won't go through it there a whole lot, but this 3rd resonant frequency for this particular sound is very low compared to all of the other sounds. It's a very salient cue. This here around 1400 hertz, where almost all the other sounds is around 25, 3000 hertz. And so you can see here. This is F1, F2. You can see how F3 starts off and then it drops down. And you go into this one. That's very steady cue. And so people had only looked at F1 to F1, F2, F3 in studying this sound and said, oh, you got all these vocal tract configurations that give you the same acoustic. However, they weren't focusing up here in the higher regions. If you look at reason being is because the energy is so weak here that people say, oh, nothing important is going on up there. However, we decided to focus on that because I observed when I was in grad student that a lot of different things are happening here. And what we found is when you make this bunch R, F4 and F5 are very close together. But when you make this pressure flux, they're much further apart. And we confirmed this with other speakers in our study that this difference is consistent. And we move on real fast to this. We did 3D modeling of the voice track. This is so beautiful. So this is a 3D vocal tract that lightning shows where the air can go in the vocal tract. And from these 3D models, we were able to extract area functions from the vocal tract. So you can see where the tongue tip is making a constriction here. That's that low point there. And then once you have, this is like 64 different area functions here that make up that model. But once you do that, this is just showing agreement. Once you do that, you can then develop very simple models. Instead of having 64 sections, now we have 4 tubes. And the reason that we want to do that is because we want to understand which resonance comes from which tube, or a combination of tubes. Because then that helps us understand what's important about the shape of that vocal tract that gives you the features we see in the physical signal. So one of the ways in which we hope to use this information is to build an assistive technology for speech pathologists who will help children learn how to produce the sound. These R sounds make up 70% of the caseload for speech pathologists. So I won't go through all the two models. If I can give you the rest of my talk. Okay. So then the next difference that I was going to talk about is just differences in the physical sizes of different people. Here's a male speaker, female speaker, child speaker, and what you can see if you look at the second and the third resonant frequencies, they're very different frequencies for these two because the child has a very short vocal tract, his resonances are higher. A female has a shorter than a male, the male has a longer. And so one of the things you can do is to develop relative measures. Instead of those early recognition systems we put in, for example, F2 and F3 information to recognize people, but given all that variability we see across speakers, it would not perform well. But if you made things relative, so instead of F2 and then F3, take the difference between them, for example. That's a simple relative measure. Another example is here when you have sub and shuh. See, I told you earlier, shuh has its energy starting very low, sub starting very high. You can think that if you were to look at a band of energy, maybe in this frequency range, you can distinguish between whether the person is saying shuh, they have a lot of energy, it's a shuh, if they don't have, it's a sub. Given you've already recognized it's a frequency. However, when we look at that fixed frequency range for males versus females, you can see there's a little bit of a difference here. However, if we normalize that parameter to that person's particular third resonant frequency, you can remove a lot of that difference. So relative measures can help you remove speaker characteristics. So I'm going to show you some results on that. And what we did is we developed the acoustic parameters for these manner features so that you could distinguish between vowels versus sonor consonants versus fricatives versus stops. So we're just doing those 4 classes of sounds. And we compared ourselves up against the state-of-the-art null frequency cultural coefficients. This is the parameterization that everybody uses. And then our kind of parameters that we developed in my lab. And here we're doing a digit recognition task. We're using that HMM, which is the state-of-the-art back-end system. And what we're doing is we're saying, if you train with only female speakers but recognize on males, or vice versa, you can see the performance using SCCs drops a lot. However, for us, we don't drop nearly as much because we're removing some of those speaker characteristics. We're making the system more speaker independent. And in this case, we train on adults recognized on children and vice versa. And these came from different databases. The adults came from this TIP children came from the TI digits. So the microphones are different. We also got channel variability. And again, our performance stays a lot higher in the MSPCs when you have all that mismatch going on. So we're on the right track in terms of trying to remove differences. So that was looking at the front end. We also developed a different back-end system, an alternative to HMMs. And this was based on a landmark-based approach. And what this means, when you are speaking and you're going from one sound to another, that leaves landmarks in the speech signal. I told you how that speech signal is constantly changing properties. So there's information that tells you when you change from one articulation to another. And so our parameters capture those changes, and we wanted to use that approach to speech recognition as opposed to an HMM. The highlights of this approach are the following. In an HMM system, all the frames have to be evaluated. However, in a landmark-based system, you only have to look at particular places where the signal is changing. You don't have to evaluate every frame. A vowel can be 300 milliseconds long. Why do you have to evaluate every frame of that vowel? Because it's steady. Nothing's changing, right? Okay. In HMM, it treats every frame as if it is independent from the next frame, as if a different person said that. Well, that's not true. The same person is talking, and we can take into account those dependencies in our landmark-based system. The HMM looks at all of the parameters all the time. In our system, we only look at those parameters that are relevant for making the kind of distinction we want to make. And in an HMM system, you can tweak and you get a better result, but you don't know why you got the better result. And our system is very transparent. You can understand why. Okay, so this is just to give you an idea of the landmark system. This is the word experience. And here are the landmarks that were found automatically. And it was based on parameters like the one I've already shown you. Here it is the aperitus and creakiness. Here are other parameters that we use, and it's clear. Here you can see that's a big change happening here. Those are landmarks. You're looking at maximum and minimum in different waveforms. And from these landmarks, we're able to actually map directly to these broad classes. Was it a vowel? Was it a stop? Was it a fricative? So we can get this sort of broad transcription of the signal. And this is where we stop. However, the next step would be, once you know you're in a vowel, go in and analyze that vowel and determine which vowel it was based on information about the tongue shape. So we built a probabilistic structure around this landmark approach where each node in our hierarchy is a support vector machine, and we only feed the parameters. We only feed the parameters for the sound or SPM that are relevant for something, determining whether something is silent or whether something is continued. So you only have like 3 to 6 parameters that go into each one of these support vector machines. And just to show you some results, this is comparing ourselves up against HMMs, and now HMMs have been worked on for decades now. They've really been optimized a lot. And this is our work, which had only been done for maybe 4 years. And so in a short period of time, we're getting results that are comparable for this broad class recognition. Okay? It's not all the way to the phoneme level. But that's just to show you the okay. Now, let me just talk quickly about some really exciting work that one of my students is doing on trying to make speech recognition systems much more robust. This is work that's funded by NSF, and it has 6 other PIs beside myself. And we're at all different institutions with all different expertise. So this has really been an interdisciplinary project. I'm highlighting myself and 2 other colleagues because we've contributed to the work that I'm going to talk about today. So the variability that this approach is getting at is something that we call co-articulation. And co-articulation is probably the hardest form of variability for a system to have to deal with. And what that is that when you're saying one sound, you're already anticipating the next sound. So you're overlapping your productions of those 2 sounds. And the degree to which they overlap can really change the physical properties of the system. And so let me give you an example in just a minute. The way traditional ASR systems have handled this, like in the HMM system, is instead of trying to recognize phonemes, they try to recognize triphones. And these triphones said, let me look at that let me model where that has been preceded by a cuff sound and followed by a cuff sound. So I'm going to take into account my immediate context when I build this model for an and I'm going to build a model for an for all the different contexts that could possibly occur. So that needs a whole lot of data to build because you got to get a lot of triphones in order to be able to model that. So this approach suffers from sparsity, data sparsity, and the contextual influence is only based on your immediate neighbors. And core articulation can go across several sounds, not just your immediate neighbors. So I'm going to give you an example of that now. So here's a person saying perfect memory spoken very clearly. Here's spoken naturally like I'm talking. And then at a really fast pace, which maybe I'm also right now, we're running out of time. And what I want you to do is to concentrate on this area right here. You can see this kind of burst here that's missing from over here. And when you see this silence here and silence here, there is no silence here or burst here. What's happening is I'm looking at three articulators here. This is looking at lip aperture, the distance between my upper and lower lip. This is looking at my tongue tip, and this is looking at my tongue body. My tongue body is the thing I use to produce the K in perfect. My tongue tip is what I use to produce the T in perfect. And my lips are what I use to produce the M in memory. And you can see these three gestures right here. So the smooth curves are what we call track variables. And these boxes, where they hit their targets, are what we call the gestures. Notice how the spacing between these gestures change quite a bit. So over here, all three gestures are overlapped. Where here, this M clearly occurs after these two. You see that? And because this is overlapped, you don't see the K or the effect of the K or the T in the physical signal, but the gestures are still there. So if you can go from the speech signal to getting to these gestures, you remove a layer of variability, right? Those gestures are still there, it's just the timing between them has changed. And so that's what we're trying to do, is to do speech inversion and get at these gestures because of its invariance property. Okay, so these are the restriction organs that we're looking at. These are the track variables that are based on these organs, and I'm kind of showing you there. So we're looking at lip aperture, we're looking at how much you protrude your lip, we're looking at how close is the tongue tip to the palate, the roof of your mouth. So you can see some kind of parameters. And these are very nice because you're always looking at some articulator relative to another articulator. So again, you're making it relative, it's not absolute. And that removes a lot of variability right there because you're making things relative. Oh, I'm actually showing the connection. Okay, so this is the speech inversion problem that we're talking about. And previously, people have used articulatory information, but for the most part, they've been looking at flesh point information as opposed to the track variables that we're looking at. When you're looking at flesh point, these are more absolute measures, and that's why there's a lot of variability in this. And so we believe that what we're doing is a lot better. And in fact, we've actually compared it to show that you can estimate us a much more reliable. Okay, so let me show you some data. Oh, this is showing all the different ways in which we want to use these track variables and gestures. We think it's going to give us robustness to speech variability. Also to noise in the environment. We submitted a proposal to even try to use them for speaker recognition. And we want to use them in assistive technology to help people who are having trouble producing certain sounds. If you can visualize what you should be doing with your vocal tract, then it should be able to help you produce sounds better. And that's whether it's a child having a hard time producing R, or someone from a different country coming here and trying to make sounds that we have in English that we don't have in their language. Okay, so in order to do this work, we've had to improvise because there is no natural speech database that has this articulatory information in it already. So we've been using this task dynamic model that was developed at Haskell's laboratory. And you give it the orthography of what you want to say, like garlic. It will go in and given this model, it can produce these track variables and these gestures for us. And we can even couple it with the synthesizer to produce the synthetic speech and hear how well it sounds. And that, listening to this and seeing how well it sounds gives you an idea of how well has it done in terms of generating this articulatory information. Okay, so we've done some initial exploration using synthetic speech, but just to let you know, we're now creating a natural speech database that is going to have this gestural information that we're creating automatically. Okay, so our goal is to realize a full ASR recognition system that that's based on these track variables and based on gesture recognition. And here's an example of how we're doing in estimating the track variables. So these are different track variables. The solid lines is the truth, and the smoother blue line is what we come up with after we smooth our track variables. So you can see we're doing a pretty good job of estimating those track variables. And we use a 3 hidden layer neural network because we can incorporate some of the non-uniqueness that you have in speech in that neural network to do a better estimate. Now we can go from those track variables to gestures, and these are just showing you the accuracy on a database. Again, trying to get to the gestures. You can see the accuracy is pretty high. And what we've been able to show so far is how well these track variables will improve ASR systems. So what we have to do, before I give you the results there, is that we train the TP estimator using synthetic speech. And we only have a small database. 900 utterances is very small for doing any kind of training tasks or speech recognition. So we use synthetic speech. We train this artificial neural network to estimate track variables. Okay? Then, once we train the neural network, we train the Kaplan filter to smooth these guys and make them smooth. Because you can see those track variables are very smooth. So we get the TVs. Then we take a natural speech database and we just use these as is because they've been trained, and we generate the track variables for all this training data. See, we have over 900 to train this TV. So look at how much speech we can do to train an automatic recognition. 8,440 training utterances. Okay, so now what we do, now that we have the track variables for all these utterances, we can now build the acoustic models for a speech recognition system. And so this is how well we work. If we add our track variables into those null frequency junction coefficients that everybody is using, that's when we get the best performance. You can compare that up to just using MFCs alone, and you way down here. And this is looking at a bunch of death functions to the CR. So we've added 8 noise types to the speech signal. Okay, and then this is comparing it to 2 speech enhancement algorithms that first cleaned up the signal before you did the recognition. So in our case, we weren't clean, we just added the track variables and we can see which do the best. Okay, and then comparing to a bunch of other front ends, adding our parameters in to these different front ends always gives you an improvement in performance. So you can see the track variables are capturing information that's not in those parameters already. So you're definitely making a difference. And this is across all those different noise types too. So it seems to be pretty robust in noise. Okay, now this is my last topic. I got a couple minutes. This is the last project I want to talk about, and this is speech extraction. We've developed an algorithm to try to clean up the speech signal for hearing purposes. So, unfortunately, I have to play this for this video. I hope you do it. Did you all hear 2 different sentences? here? Is there anybody else here? Or would you make sure turn up the volume on? Okay. And they're picking out when they have it on. Oh, wait a minute. Oh, you are. I want to make sure I'm putting it in the right place. I'm never playing around with it. How many? Oh, there you go. Is that good? One more time. Okay, well, here's the extracted. And then this is the master signal that so you hear a little bit of leakage in the weaker signal, but in the stronger signal you don't hear the leakage. Okay? Let me go here. Now here's when the noise is not speech, but in this case it's subway noise. So it has characteristics very different from speech.
That's always the technical trait, always goes along. That's always the technical trait, always goes along.
And here's when you have a lot of people in the background.
That's always the technical trait, always goes along.
That's how you got to hear it.
That's always the technical trait, always goes along.
Okay, and this is real situation where we can gear ourselves up just from other technology. But we recently did intelligibility test for the case where you have two people talking. So it's either two male speakers talking, two females talking, or a male who's the target speaker with a female, or another male. Oh, wait a minute. I'm sorry. It shouldn't be here. Well, this is male, female. Don't pay attention. Male target, female master. Female target, male master. This is male, male, female, female. So these should be hard because they're both of the same gender, but these are different. And this is looking at different signal to noise ratio. This is -3 dB, 0, 6 dB for the cases where they're different. And then 0, 3, and 6 dB for the cases where the genders are the same. And the red is before we process, and the green is after we process. And you can see we are making some improvements. I would like for it to be higher, but we are making some improvements in intelligibility. Not at 6 dB so much, because at 6 dB, we don't have any trouble at all separating two people. This is loud enough. The difference is large enough that we don't have a problem doing that. We more so have a problem at 0 dB and definitely -3. So at the lower end, we're seeing a difference. And then well, that's effective because those were undergraduates coming in and doing tests. And this is using pen scores, which is a standard in the literature where it doesn't require people to come in. You're supposed to try to estimate what listeners would do if they were taking the test. And so here is unprocessed in blue and the processed in red. And the only difference in the green and the red is that in the red, it's totally our processing. In the green is where we've taken the constant information from the clean signal and put it in there. Because we wanted to see how well are we actually doing those constant readings, because that's the hardest part for us. And you can see we definitely get an improvement if we could separate those consonants and so that's going to be our goal, is to work further on the consonant information. But you can see the test scores are increasing. So it says that we are improving quality. Okay, so I'm going to end there and take questions.
So, Carol, as far as I can figure, the output of your system is phonetics, right? Or is it, you want to eventually get the word?
Oh, yeah.
So is word, as I understand it, you're first recognizing phonetics, and then you're going from there to words, or?
Well, no. So I talked about two recognition systems. One was the landmark recognition system. That was the first one that I talked about. And it wasn't even going to phonemes, it was going to broad class. So it would say, this is a vowel, this is a fricative, this is a stop. Okay? And because the digit recognition task is so small, there's only 0 through 9, they differ enough just based on their broad classes alone, and if you recognize the broad classes correctly, you can recognize what digits correctly. So we can train a problem like this. Okay? We put that probabilistic framework around it so you could scale it up and put a grammar with it, because you need higher level knowledge to get to words. And most of the work done during those alpha projects was at the higher level, building bigrams and trigrams, and figuring out how to use that to do better recognition. And we're trying to show that you can do a whole lot better if you also concentrate on the low-level knowledge, information in the speech signal, not just looking at language models. Okay, so that was the purpose of that. Now, in the work that talks about using articulatory information, that is that's doing word recognition. There, that's not doing phoneme recognition. Okay, so that's a standard full-blown H&M system, which is the state of the art. And all we've done is, in addition to the male-producing capital coefficients that everybody uses, which is the state of the art, we added on to that these track variables. We said, how would that improve recognition if we had this articulatory information? Now, ideally, instead of track variables, we actually want to put in gestures. And that's what we're working on, going from those track variables to the gestures. Because the gestures are the things that give you the most information. They're telling you where are those constrictions in the local track. How well have you reached those targets? And when we get to gestures, we don't even want to, we want to try not even using even gestures, gesture information, and how well will that give you in terms of constriction. That's where we're at.
It seems like you have two very different paths. One is the gesture extraction, the other speaker recognition. And the information you might be throwing away when you normalize for getting the word information, gesture information, maybe something you want to preserve and do or protect.
The speaker. Oh, definitely.
So are these really complement research programs? And I guess I was curious specifically about the two different R's for the bunch and rest of it. Is that common that individuals have different ways of producing common sounds?
Oh, no. R is a very unusual sound. No, nobody, I don't know another sound. Oh, L also is very unusual. That's another one of the vowel-like sounds like R, right? That people hadn't built models for, and actually we have built a model for that. I just didn't have time to do it. Shinwei did work on that sound as well. Because what happens in an L sound is you raise the sides of your tongue so airflow goes around the side. But you can just raise one side, or you can raise both sides. And that creates, whether you have one channel versus two channels, and whenever you have alternative channels, that gives you more resonances and interests. There's a whole new zero, so you can really change the acoustic characteristics quite a bit. So the R and the L should be very good sounds to use for speaker recognition. Another sound that's really good for speaker recognition are your nasal sounds. Because when when airflow is going just through your nose, you have these sinus cavities coming off of the nasal tract, and everybody's nasal cavity sinuses are going to be different. So the size of those sinuses is going to change the properties, the poles and the zeros of that sound. So Tarun actually did a lot of work on nasalization and looking at the effect of these sinuses. And people have shown previously that they're very good sounds for speaker recognition. So some sounds are better for speaker recognition than others, and that's what Jaime is going to be working on. He was here earlier. He's doing speaker recognition, and he's going to be focusing on just using not all of the sounds, but these particular sounds that should show a lot of variability across the Well, we haven't been worried about real time so much until this year. Because we have a cluster. And it's all research code. Right. If you have good software engineers, you should be able to do this full time. Right. Oh, okay. Well, because your hearing loss is mainly in the higher frequency, and your consonant information is mainly in the higher frequency. So you're losing a lot of consonants probably as you get older. Yeah, but what they're doing is they're not only amplifying the signal in that region, they're also amplifying the noise in that region. The only way that they improve the signal-to-noise ratio in hearing aids is to use dual microphones. And those, because you can take advantage of the spatial separation of the microphones, you can reduce the noise. But there's no single channel noise suppression algorithm that does each of these things. But that, I think, we just submitted a proposal to NIH to work with hearing aids and both the implants. There it is. And we're trying to work exactly on that problem.
Very good.
With what? Yeah. But if you put enough knowledge in there, they can. Because you're not just processing bottom up when you do speech recognition. You're also processing from top down. So you are using a lot of information about what that person has already been talking about. You fill in a lot of yes. You use a lot. So a good example is when you're talking on the telephone channel only gives you frequencies between 200 hertz and 4,000 hertz. But there are a lot of sounds, well, constant sounds, that have energy above that. You're not getting all of that energy, but you have no trouble hearing because you feel it in. The brain is an amazing thing.
So if you're looking at detecting phonation types, streaky versus modal versus graphic on American English. Now there are some languages like Vietnamese and Hmong where these are actually phonemic but graphic.
Yeah.
Have you run any experiments on that?
I have not done that yet. They haven't had that feedback. Earlier. And let me just say, especially to the young people, because they're expecting, like, I think worldwide, there are like 200, almost 300 million people with moderate to profound hearing loss. They're expecting that number to double, not only because people are living longer, but younger people are starting to need hearing aids 20 years younger than their parents because of those MP3 players where you're playing the music so loud all the time and going to really loud concerts. They don't realize all of the damage they're doing to their ears when they do that. So, caution you guys about loud noises.
I'm curious to get your perspective on where you think the big breakthroughs in speech recognition accuracy are likely to come from, especially whether they'll be algorithmic breakthroughs or more creative use of sensor data, like say in these mobile phones we all use a camera pointed at your lips to get lip movement.
Well, I think you want to probably do all of that because I think humans are doing all of that. And as I'm listening to you, I not only hear what you're saying, but I see your mouth moving. That's additional information that we know will improve speech recognition if we have that. But I also think that new approaches speech recognition. We've been locked into doing the mid-Markov modeling for so long. And that was all needed to optimize that. But I think that people need to start thinking about new things, new paradigms for doing speech recognition. And I think hopefully we're going to have a new paradigm that's based on dynamic Bayesian networks soon, using this articulatory information that we're trying to get. But people need to pay a little bit more attention trying to understand the variability there and use machine learning techniques. And Vikram has been excellent at this. Understanding the nonlinearities and the non-uniqueness in the signal and seeing what would be the right machine learning technique that will model that for you. Okay, so not just blindly using, throwing a lot of different techniques in, but really thinking about what's going on and trying to match it up with the techniques that we have.
Well, let's thank our speaker one more time. Refreshment in the back. Halt yourself. Al is going to stick around for a while, so feel free to come up.